Unit 11 exam, Section 7, similar solids. Here we're going to go ahead and try to set up ratios of various side lengths or one-dimensional shapes to ratios of areas, ratios of volumes, and then also maybe trying to find a radius or find a height using these ratios that we had set up. So very quickly, if we take a look at what we had discussed in class, we're really looking at three different scenarios. We're looking at setting up a ratio of sides or heights or radii. Again, really here what we're looking for is one-dimensional measurements. So in this case, given yards. Then we're looking for ratios of areas, surface areas, or lateral surface areas, which in this case would be units of yards squared, sticking with the yards theme. And then volume, of course, is a three-dimensional, giving us yards cubed. So the way we had set this up was if I gave you a ratio of side lengths or heights or radii was A over B, well, it made sense then that the ratio of the areas was A squared over B squared. Yards became yards squared. Then A over B became A squared over B squared. Going one step further, if A over B, we went to volume, we would have A cubed over B cubed. Just as yards went to yards cubed, A over B went to A cubed over B cubed. We talked about how these relate, going from sides to areas and back again. I said going from A over B to A squared over B squared, we would square both the numerator and the denominator. And if I wanted to go backwards, we would in fact take the square root. We also talked going from sides to volume. It meant that we would cube our values, and then going back means we would take the cube root. We also discussed how there is no direct link between area slash surface area slash lateral surface area to volume. So we have to always go back to sides and then go back out to volume if we're doing such things. So this relationship is what is the premise for everything that we've been doing or going to be doing on these problems. So let's jump into it. 7a, the two spheres have volumes of 64 pi centimeters cubed and 729 pi centimeters cubed. What is the ratio of the radii of the small sphere to the radius of the large sphere? Okay. First of all, I'm given a volume value. So let's create a ratio. And we always look to reduce first. Here are the only things I can divide out. So where are we trying to go here? Well, we're trying to go to the ratio or ratio of radii, which if we go back over our organizer here, we see that if I'm going from a volume, I want to go to a ratio of radii. So volume to radii, we would in fact have to take the cube root of our values in the ratio. Meaning we're taking the cube root of 64 over the cube root of 729, which gives us a value of 4 over 9. Ratio of my radio is 4 to 9. Plugging this into the way, this is what it looks like on an SOL. A lot of the time they'll ask you to plug in the ratio 4 to 9. Now notice it specifically tells us I want the small sphere to the large sphere. So the smaller number here is going to be 4 to the large sphere, which is 9. So I'm choosing these values. We would have to, on the SOL, we'd have to actually click these values and then click and drag these values in here. We're just writing them in. Okay, B, two spheres have surface area of 169 pi centimeters squared and 49 pi centimeters squared. Right off the bat, we again see that we are given surface areas. Let's make a ratio here. Once again, I'm looking to reduce these numbers, but I can't. The only thing is I can divide out are the pi's. Here, what we're trying to go to is what is the ratio of the volume? We want to go to the ratio of the volume. So looking at our chart again, I'm currently in surface area, ratio of surface area. I want to turn this into a ratio of the volumes. Well, how do I actually go about finding the ratio of the volumes? Well, there is no direct connection here from areas, surface areas, lateral surface areas to volumes. So I must first go back to sides by taking the square root, get that ratio, and then cube it to get the ratio of the volumes. So let's go ahead and take a look at what that looks like. So converting from surface area to sides, we would take the square root of both numbers. Square root of 169 is 13, square root of 49 is 7. Now we're going to go ahead and turn these into volumes, meaning that we want to take this 13 over 7 and cube it. So we get 13 cubed over 7 cubed, which is a ratio of 2,197 to 343. I look to reduce this down again. It cannot. So this is my ratio of volumes. Okay, Example C, two similar cylinders have heights of 45 meters and 20 meters. What is the ratio of the volume of the large cylinder to the ratio of to the volume of the small cylinder? Okay, right off the bat, we know that we are given two height measurements. So let's set up a ratio of these heights. 45 over 20, which in this case we're looking to reduce here. We can divide both by 5, and we mean 9 over 4. Again, we're looking to reduce. What we want to do now is we want to turn this into a ratio of volume. So to go from heights or one-dimensionals to volume, three-dimensional, we're going to cube 9 over 4, so I get 9 cubed over 4 cubed, which is equal to 729 over 64 is my ratio of volumes. Okay, last problem, slightly different, but still the same idea. 2,000 pounds are similar with a large cone having a volume of 1,372 pi and a small having a volume of 108 pi. If the radius of the small cone is 6, what is the radius of the large cone? Okay, so right off the bat, again, we are given a volume ratio. Go ahead and set that up. Which we want to actually reduce. Here we can divide out the pi's and we can reduce this down. Get 343 over 727. So what we want to do now is I'm given a radius measurement. I'm given a radius is equal to 6, and we're asked to find the other missing radius. So this volume ratio is no good to me unless I can turn it into a radius or a one-dimensional ratio, which I can then compare up with my last statement, what we're trying to find. So we need to go ahead and turn this into a side measurement or a radius measurement. Meaning we're going to take the cube root of each of these, 343 and 27, which means that my new side ratio is going to be 7 over 3. Now I'm going to highlight this. It's not our actual answer here, but 7 over 3 will be helpful as I find my answer. Well, I know that the radius of the small cone is 6. I want to find the radius of the large cone. So I really want to set up here is a proportion where we can take this 7 over 3, which is the ratio of the volumes reduced down or transferred into the ratio of the sides, 7 over 3, and use the 6 inches of the radius of the small cone. Well, the 3 was our smaller volume, so we can set the 6 inches with the smaller volume, and then we want to actually figure out what this radius value is going to be. Well, once again, notice a quick note on this, I set the large values over the small in terms of how my volume that were reduced into sides or changed into sides, and then my measurements of the radius. We know that this, since it's a larger cone, it's going to have a larger radius than the 6. So here, this is just a simple cross multiplication, which we're going to go ahead and do now, yielding 7 times 6 equals 3 times x, or 42. Radius of 14 inches. This is a little different than what we've been doing, where we're actually going to take the volume ratio into a side ratio and then use it for something else. On the classwork, we did a few examples where we used the ratio after we changed it to maybe go ahead and find a volume or find a certain other thing. So example D is probably one of the more challenging problems, just because we're not just finding the ratio, we're then using it and applying it to a different problem. So check that out and the classwork as well.